Okay, so as I said, what you're going to see on the test is you're going to be given the original function, you're going to be given the first derivative, and you're going to be given the second derivative. And you're going to be prompted to do all of those things on that list that I showed you on the first slide. So number one was the domain. We look at our original function. What is the domain of this function going to be? And basically what you're looking at is, are there any points where our function is not going to exist? What do we think? I see a bunch of people shaking their heads. I see, yeah, this thing exists everywhere, so we can just say x is an element of the real numbers. The set of all x, such that x is an element of the real numbers. Second step, we move on to our asymptotes. Our vertical asymptotes and our horizontal asymptote. So for our vertical asymptote, remember, we are looking for where the denominator is equal to 0. Okay? And this, of course, relates closely to our domain, where we were looking for places where our function doesn't exist. So if we take our denominator and we set it equal to 0, and then we solve for x. Can we solve this thing for x here, Adam? No, there are no solutions. So that's telling us right away that this particular curve has no vertical asymptote. So I'll just write none under vertical asymptote. Next up, horizontal asymptote. Okay? You can use whatever technique you want to find your horizontal asymptote. I'm going to think about this in terms of limits. So I'm going to take my function here. I am going to take the limit as x goes to positive or negative infinity, but I'm going to divide each term that I see in here by the highest power of x. My highest power of x is x squared, so I'm going to end up with x squared over x squared minus 1 over x squared, all divided by x squared over x squared plus 1 over x squared. If I simplify this a little bit, I get the limit as x goes to positive or negative infinity of 1 minus 1 over x squared, 1 plus 1 over x squared. Now, those 1 terms aren't going to change as we change the value of x, so they're just going to stay as 1s. What's going to happen to these terms that are 1 over x squared as we take our limit, Luca? They're going to go to 0. So we can essentially just say that's going to go to 0, that's going to go to 0. So our limit is going to be 1 over 1, which is just 1. So this tells us that our horizontal asymptote is going to be y equals 1. Of course, you could have done that right from the beginning by looking at the order of the leading terms in the numerator and the denominator. You see that they're the same. That tells you that it's y equals 1, if you can remember those rules. However you get your horizontal asymptote, that's good. All right, what was step 3 here? Oh, our x and our y intercepts. So, y-intercept. Think back to grade 9, think, okay, get the y-intercept. What do we need to do, Adam?
Sub-0 for x.
Yeah, we set x equal to 0, and then we solve for y. So we look at our function here, and we think, okay, I'm going to put in x equals 0. What do I get for y? Well, what do I get? Well, I get 0 minus 1 in the numerator, which gives me minus 1. I get 0 plus 1 down in the denominator. That gives me plus 1. So that just equals negative 1. So my y-intercept is going to be the point 0, negative 1. And so I could add that to my graph when I get to the graphing stage. What about my x-intercept? How do I find my x-intercept here, Luca? Yeah, so I'm going to set y equal to 0, and then I'm going to solve for x. So let's see, y equals 0. Now, if I'm setting y equal to 0, and I'm trying to solve I'm only interested in the numerator, okay? Because the denominator, I can imagine sort of cross-multiplying x squared plus 1 times y. That's just going to multiply to 0. So really what I'm looking to solve is 0 equals x squared minus 1. Because x squared minus 1 is my numerator. Okay. Can we solve 0 equals x squared minus 1? What do you think, Omar?
Yeah, I think so.
How should we solve it?
0 equals left pairing x minus 1 right pairing left pairing x plus 1 right pairing.
Exactly. He is factoring this thing. And then he's going to see that his solutions here are positive and negative 1. Okay. So we've got 2 x-intercepts, and we have got 1 y-intercept. What are we on to now? Okay, we are now looking at 4 and 5. So I'm going to give myself a new page, and we're going to think of 4 and 5 together. So 4 was find our turning points, or our local maxima and minima. 5 was to look at our intervals of increase and decrease. So if we're going to set up our interval table here, what's the first thing that we want to do? What do we need to find to set up our interval table? What do you think? There. Yeah. Y primed equals 0. Y primed equals does not exist. We call these things our critical numbers, or our critical points. So let's see. If we set y primed equals to 0, we're going to have 0 equals 4x over x squared plus 1 all squared. Okay. How do we solve something like this? What do you think, Arham? Well, we can cross multiply without expanding. So if we cross multiply, what are we going to get? 4x equals 0. Yeah, so again, we're only interested in the numerator here. And what's our solution to this? X equals 0, yeah. So one of our critical numbers is x equals 0. Are there any points where y prime does not exist? Well, let's see. Y prime doesn't exist. We're interested in where the denominator of our derivative is equal to 0. So our denominator here was x squared plus 1 all squared. Are there any points where that denominator is going to be 0? What do you think, Luca? No, there's no solution there. So we can just say no solution, or put an x or something like that. Okay. So we have one critical point. So let's set up our interval table here. Our intervals are going to be from negative infinity to 0, then from 0 to positive infinity. And we are checking the sign of each term in our first derivative. So 4x and x squared plus 1 squared. So let's see. 4x, if x is negative, 4x is going to be negative. If x is positive, 4x is going to be positive. This term that we have down in the denominator, because the whole thing is squared, this is going to be positive no matter what we do. So our derivative is going to change sign from negative to positive at x equals 0. And in terms of our original function, it goes from decreasing to increasing. So what do we have at x equals 0? We have a local minimum. Now we know the x value is 0. So for the purposes of making our graph, we're going to take that value, that x value of 0, sub it back into our function to get our y value, because we want to be able to plot that point on the graph. Luca? Do we? Okay, so what is the y coordinate? -1. Okay, so it was pretty easy in that case. So we've got our local minimum. We know where this thing is decreasing and where it is increasing. Next up, we want to do the same thing for the second derivative, and we want to investigate our points of inflection and our concavity. POI and concavity. So if we're interested in points of inflection, we are interested in where? Well, in where what? What are we trying to find here? Luca. Or, yeah. Y double primed equals 0 are possible points of inflection. Y double prime doesn't exist are additional places where it's possible that the concavity changes. So, if we want y double prime equals to 0, let's just set 0 equal to our second derivative here, which is -4 times 3x squared minus 1 divided by x squared plus 1 all cubed. Okay. What part of this are we interested in being 0? Adam? The numerator, yeah. I write the whole thing out here because just so I have a copy of the second derivative on this slide. You don't have to write it out. If you just say, I'm setting the numerator equal to 0, and then you go from there, that's good. So let's set our numerator equal to 0. But our numerator is only going to equal 0 where this term in brackets is equal to 0, because that's the only place we have an x. So let's do 3x squared minus 1. Okay. And how do we go about solving this thing? I don't know. I'm going to take a pause here, and I'm going to write numerator equals to 0. How are we going to solve this guy here? Bryn, what do you think? Okay. And then divide by 3. 1/3 is x squared. Take the square root of both sides, and what do we get? Root 1/3? Special triangle. No, not a special triangle. What do you have to remember when you are taking the square root of something that is itself squared? Positive or negative. Yeah. So and this is important here because this means we have two possible points of inflection, two critical numbers to use in our concavity table here. Okay, what about where this thing does not exist? We imagine setting our denominator of our second derivative equal to 0. Any solutions? X squared plus 1 all cubed equals 0. What do we think? There? There are no solutions. Okay. And you might sort of notice a pattern here. When we did where does our first derivative not exist, we had no solutions. When we looked for our vertical asymptotes and we said where does our original function not exist, we had no solutions. So there tend to be sort of a trend in terms of finding where there are no solutions to these things. Okay, our concavity table. We are going to set up our intervals here. So we're going to have negative infinity to negative root 1/3, negative root 1/3 to positive root 1/3, and then positive root 1/3 to positive infinity. And remember, we are checking the sign of each term in our second derivative. So we have two terms up in the numerator, -4 and 3x squared minus 1. And we've got one term down in the denominator, x squared plus 1 all cubed. and we want to figure out how the sign of our second derivative is changing. All right, the top row is the tough one, so I'll fill that in. What about the second row? 3x squared minus 1. Okay. So imagine putting in a really big negative number, like negative 100 or something. Is 3x squared minus 1 going to be negative or positive? What do we think? There. Positive. Yeah. We square that negative number, and it makes a big positive number. What if we put in something between negative root 3 and positive root 3? Well, we can always imagine throwing in 0 in this case. And what do we get there, Bryn? Negative. And then in the third column, we can imagine putting in a really big positive number. But when we square it, it just gets even bigger and more positive. So we're going to have the same thing that we had in column 1. Positive again. What about this third row here? Now, if we were squaring the whole thing, we know it would be positive everywhere, because squaring it, well, multiply a negative times itself and you get a positive. It's not so clear-cut with cube roots, because if we get something that's negative inside here, the final answer is going to be negative. But we're helped here a little bit. What do you think, Omar?
No, because there's a squared inside the cube.
Yep, so whatever we put in for x, even if it's negative, we square it. That's going to make it positive, that x squared. And then we're just adding something to it. So it's something positive plus something else, which is still going to be positive. We cube it, it's still going to be positive. So we end up with, no matter what x is, this is going to be positive no matter what we do. So our second derivative is going to be negative, positive, and then negative. What does this tell us about our function? Well, it's going to be, let's see, second derivative is negative. Is it concave up or concave down? Let's take a poll. Who says concave up? Who says concave down? Everybody says concave down. Excellent. Yeah, so it's going to go concave down, concave up, concave down, which tells us that we have 2 points of inflection. Okay. At, let's see, and we want the coordinates of these guys. So I've got root 1/3, negative 1/2. Sorry, negative root 1/3. No, still negative 1/2, sorry. And positive root 1/3, negative 1/2 again, just by subbing that back into the original function. Now we want to take all of this information we've got and put it together to graph our function. So we start way back at the beginning here. The first thing we figured out was our domain. So we know that since our domain was all the real numbers, basically our graph is going to cover this entire x-axis here. We figured out our vertical asymptote. We didn't have one, but our horizontal asymptote was y equals 1. So let's add that in. Then we figured out our y-intercepts. Let's see, our y-intercept was -1. So let's add that point on here. We had 2 x-intercepts at +1 and -1. So these are points, so we can add them into our graph as points. What else did we have? Well, we knew that we had a local minimum at x equals 0. So we know that at this point right here, this thing is going to go do something kind of like that. It's a local minimum. We know that from our increasing decreasing table that our function has to be decreasing on this side of the y-axis and increasing on this side. Okay? So all the way from negative infinity to 0, our function has to decrease. So that kind of makes sense, because if it's got to approach this horizontal asymptote here, it's got to start here like this and end up going down like this. And if it's going to approach this horizontal asymptote over here, it can start coming up here and head along like that. So at this point, we can kind of visualize what this graph is going to look like. But let's just make sure that this is consistent with the information that we got from our concavity table. It says that we had 2 points of inflection at, let's see, negative root 3, negative 2. So that's somewhere in here. See how I can label this thing. Negative root 1/3, negative 1/2. Okay, and then we had another one over here at positive root 1/3. Whoops, that's a 3. Still at negative 1/2. Okay, that makes complete sense here. So let's just connect the dots. And there's our graph. And see if it matches what we said in our concavity table. Our concavity table tells us that this thing starts off concave down, in the middle is concave up, and at the very end, it ends up concave down. Does this all check out? Yeah. This is concave down up to about here. In between our 2 points of inflection, it's concave up, and then it switches over to being concave down again. And there's our graph. Okay. So we could have, if we wanted to, stopped after we did that increasing, decreasing table and sketched our curve. Remember, on the test, it's going to ask you to do everything. Okay, so just run out the string and you've got your graph. Okay?